So far, we've only discussed general antiderivatives. That is to say, if I start off with some little f of x, I can find a big f of x, and then there's the plus c to get a general antiderivative. But it's often the case that we want to solve for specific antiderivatives. We say that instead of saying, oh, it's plus some constant, I want it to know whether or not it's plus 3 or plus 2.5 or minus 100. I want to know what the value of that constant is. And that happens in what's known as an initial value problem. So what you might want to know, for instance, is a function that maps the position of a particle in space. And you may know how fast it's moving all the time, but where it's in space is a function of where it starts, because it could be going 100 miles an hour, but if it started 100 miles an hour here versus starting 100 miles an hour here, the general function of its position the position functions would be similar, but they would differ because their starting points differed. And that's the basic idea behind an initial value problem. So again, we can find that if we are given specific information. Now, I also want to note that generally we've only worked with little f and big F, but antiderivatives have a natural relationship to derivatives. So if I am given information about its derivative, then f of x plus c is the general antiderivative for f prime, right? Because the derivative of this is f prime, because that goes to 0 and that's derivative is f prime. So what am I saying? I'm really saying that if we start with f prime, we can just take antiderivatives to work our way up. And in fact, if we start with f double prime, we have to take 2 antiderivatives to work our way up. So that's kind of an interesting case. Anyway, let's get started. I need to find a function where f prime of x is 4x and f of 0 is equal to 5. So the way we're going to do this is we're going to find the antiderivative. So if f prime is 4x, then f of x, we have to do the power rule here. That gives us 2x squared plus a constant. But we want to figure out what that constant is, because specifically we have an extra piece of information. We know that at 0 the function's output is going to be 5. So f of 0 f of 0 is c. So that tells me that c is 5. So when I say what I want is a particular solution, in this case, the particular solution is five. That means that, notice that in this particular solution, if I take its derivative, I still get 4x. And I satisfy the condition that when I plug in 0, I get 5. So initial condition, you can only find particular solutions when you're given that extra piece of information. If I wasn't given this piece of information, I would have no way to find that particular solution. So that's one way to know that you're dealing with initial value problems or particular solutions. Those are kind of used interchangeably. Usually initial value problems start at like 0 because that's the initial value. You start at like time 0. But those are really, they're one and the same, so I just want you to be aware they're used interchangeably. In this case, I have f double prime, so that's a little bit odd. So what I'm going to do is I'm going to work my way back up. I'm going to say f prime, so I've got to find something where the second derivative is 3x squared, so that tells me that the first derivative is x cubed, and I'm going to call this constant c1, and you'll see why in a little bit. X cubed plus c1, and that's going to be because I added 1 to the power and then I divided by that new power, so the 3's cancel. And I know that f of negative 1 is negative 3, or f prime of negative 1. So that's going to be negative 1 cubed plus c1, which is negative 1 plus c1. But I also know that the output is negative 3. So that tells me that c1 has to be negative 2. So what I'm going to do now is I'm going to rewrite this with this information. So I'm going to say x cubed minus 2 is f prime of x. Now, a good thing to do at this point is to just verify that you've done it correctly. If you take its derivative, you'll get 3x squared plus 0, which is correct. And if I plug in negative 1 here, I get negative 1 minus 2, which is negative 3. So I can feel like I'm on the right track. However, I have f prime, and I have information about the original function. So when I take its antiderivative, I add 1 to the power and divide by the new power. So I get added 1 to the power, divide by that power. I had negative 2, so that antiderives to negative 2x. And then I get another arbitrary constant. So in this case, I could have chosen them both to say c, but I don't want that to be confusing. So I'm going to call this the first one, or c1, and this to be the second one that I'm going to call c2. Now I have this information that f of 2 is 5. So that f of 2 is 5. When I multiply this out, 2 to the 4th is 16, divided by 4 is 4. 2 times 2 is 4, obviously. So that leaves that C2 is just 5, so we didn't actually have to work that hard for this one. And that's our answer. But we want to check that answer. So we take its derivative, we get x cubed minus 2. And then we can plug in, and so since that derivative is that, we can feel reasonably confident. If I plug in 2 to this function, I get 4 minus 4 plus 5. I feel good about that. And then I can continue to take a second derivative to make sure that I get back to here. Sometimes you may want to solve it all the way through and then go back and check. I don't really recommend that, because if you can check things along the way, you can stop the process easier instead of propagating an error and having to wait till you're done to figure out anything's wrong.